There's this meme that every OP GoF design pattern can just be replaced with a function. If you think about it, it's not that funny. Sure, there's some truth to that, and some patterns are already obsolete, but we also don't just use functions in a vacuum. We write, compose, and manipulate them. Plus, jumping into those kind of extremes is not helping anybody. We can build connections and grow on top of existing knowledge. So I thought, what if I just go through all 23 patterns and see which one I actually use or see being used and what the functional alternatives are, if any. We start with creation patterns, and the thing is that outside of OP, there's no really OP classes, so making instances of classes doesn't really make sense. But we can still talk about it, and we can abstract over creating instances of things. Instead of classes, we'll be thinking in terms of modules, bundles of functionality, encapsulated APIs, or something along those lines. Abstract factory. Provide an interface for creating families of related or dependent objects without specifying their concrete classes. I learned it by heart as a way to make bears, airplanes, and cars out of different materials, out of wood or plastic and so on. But in the OP world, we can use this to abstract over things like database connections and commands while generalizing over databases. So we can write code that creates a database connection, executes some queries, and runs it with one database. Later, if we want to or need to, we can swap the database by swapping the factory and configuration, and the code stays the same. In FP, on the other hand, we don't use abstract factories, we utilize functions and polymorphism, polymorphic types, and in some cases type classes. Let's take a look at two Haskell libraries and how they address this. We start with Beam. In Beam, we write abstract backend database agnostic code in terms of monad Beam with polymorphic backend and generic functions. Here's the simplest example. Don't worry about the function signature for now. The important part is that it's abstract in terms of the database. There is some monad Beam and M, which is abstract. The B stands for the backend. So the code, the implementation doesn't care. We say, here's some database and product table, and we select all of them, and we'll run selecting results to select all products. It might look awkward if you haven't seen this before, but once again, ignore the specific. Think about the abstractions and the general picture. We can then execute for a specific database using one of the backends. For example, we can use run beam Postgres for Postgres, pass the connection, and run that query 1 that we saw, query 1. And note that we can use the specific backend directly if we want to access the full power of the database and mix and match abstraction and concrete things. If you want, you can see the usage example in the docs or in the linked repository. Another library I want to show is Persistent. It's somewhat similar. We use functions that are abstract over the backend type. For SQL databases, it's data SQL backend here. This library uses type classes such as persist_storeRead and persist_storeWrite to define database operation. Simplest example, we use insert. We create a specific product and insert it right away. The insert returns an ID and we print the ID. The example is very simple. The interesting part is the signature. This time we have monad.io_m and we have reader T with SQL backend. This last part is an interesting one. It means we can access database configuration. For example, database connection can perform arbitrary I/O operations and don't return anything meaningful. This parenthesis means we return void. This is not really for us, it's for the compiler and for the library. This is gonna interact with insert and whatever insert expects. Once again, for us, SQL backend stays abstract. When we want to tie everything together, we use a specific backend. For example, we can use SQLite. Here, example of the run function. It takes a connection string and it also takes the database action, the one that created before, the reader T with SQL backend and whatever else, doesn't matter. Or if we want to, we can run it with some pool, for example, with Postgres SQL pool, takes a connection, takes number of connections to keep open in the pool, takes a pool with SQL backend. As you can see, it's mostly abstract, but at the end we tie to the specific implementation, and if we want to, we untie it and retie it with a different implementation. Most of the time we keep it abstract and only use simple things that like insert or whatever, but we can also use specific things, so we're not limited only to generic operations, which is pretty convenient. Factory method. Define an interface for creating an object, but let subclasses decide which class to instantiate. Factory method lets a class defer instantiation to the subclasses. In the simplest form, we want to hide the concrete implementation, so it can be created, returned, and used behind an abstraction or an interface, a somewhat simple and a common use case. Imagine we have some payment processes system and need to implement multiple providers. For now, just Stripe and PayPal. This is an example of so-called tagless final approach, a popular approach to structuring code in Scala. We have an abstract interface, payment processor with some generic F, It's just generic. And somewhat abstract implementation. This time F has a sink, still generic, a bit less generic, but we still don't commit to the final implementation. There's some abstraction there going on. It could be simple I/O, we'll talk about I/O later. It could also have explicit error handling. It could have explicit tracing, logging. We can put as much bells and whistles as we want, but we don't care about those implementation bells and whistles right now. We only care about the logic. So we keep it abstract and a bit less abstract. Sorry if it's too confusing. The idea is that we have payment processor interface and we have more specific but still abstract implementation. Imagine you have an interface and then two abstract classes. It's still abstract but somewhat specific. Anyways, let's keep exploring. If we delegate the creation of the specific implementation to the payment processor factory, for example, based on the configuration, we get ourselves a simple factory. There's some configuration, in this case, very useful. You just put a string in there. You can read it from the environmental variables. You can read it from some other config, whatever. We pass the config to the factory and the factory decides if it's PayPal, create one. If Stripe, create the other one. And then you're going to get a payment processor. We can throw errors, can do any validations we want, but it's a factory. Because we can always go a level deeper and abstract the abstractions even more. We can abstract over the factory, and instead of having just factory based on configuration, for example, if the configuration is not from configuration files, but from some experiment provider or experiment service, whatever they're called, you can also do different ones based on the user country that fetches from some different service and then determines which payment to create and so on. Tons of options here, but let's not get too wild. Instead, let's look at a primitive usage example so we can finish with this example. Note that there is nothing about specific implementation stills. We're still quite abstract. It's one-to-one right now. The make payment calls process payment and refund payment calls refund. But before doing this operation, first we create the processor based on the configuration, based on the provider, based on the factory. The factory decides which implementation we create. In each case, they could be different for different things, and then they perform the operation based on the one they created. Plenty of fun here, I know. Factory methods are still used in different shapes and forms, especially in the Scala world. I have a couple of similar things in production. As soon as you have something more interesting than just functions, as soon as you have tagless final, MTL, service patterns, if you haven't heard of those, we're gonna slowly reveal and talk more in details about each one later. But if you have any of those, factories spread out naturally when we actually have multiple implementations and we want to decouple logic from bells and whistles or logic from different abstractions of logics. Singleton. Ensure a class only has one instance and provide a global point of access to it. In the presence of immutability and other things, singletons are not really needed. Most of the time we create something just once and then pass it around, knowing that nobody can modify it. Let's look again at the beam example. Here we have a function called withConnect that takes a connection info, takes some block of what to do with the connection, the function opens the connection, and then does some operations that we're passing here, and then it closes the connection. The important part here is there is one connection that it has, and then we pass it to all the function. We pass it to cleanup, we pass it to query data. So we create the connection once, and then we pass it everywhere as much as we need. Not really singleton, but it pushes us in the right direction. Usually, if you want something similar plus modification on the top, you're gonna have the connection wrapped in something like IORef, and then you're gonna pass it all around, and then you can modify it concurrently or read it concurrently with IORef. And you can see ref and other concurrency primitives in different libraries. In PureScript, there's gonna be one in cats also called ref, and in Haskell there's IORef and other things as well. However, if we are in Scala land and you're coming from Java or OP, and you do need the simplest form of singleton, where you just have one instance of a class and you just want to reuse it, you don't need the double-threaded save, the concurrent proper singleton. If you don't need that, there is also singleton object. For example, in the documentation talk about logger, you have a logger which is an object, a singleton, and that has one method. And then in somewhere else in the project, you just import the singleton logger info, and then you reuse it. Depending on what kind of singleton you want, there are different approaches and different things. Builder separates the construction of a complex object from its representation so that the same construction process can create different representations. We just talked about Scala, and builders are also quite common in Scala. It's one of the patterns that the community inherited or carried over from Java. For example, let's look at the request definition using the STP library, one of the most popular HTTP clients. If we want to create a request, we add a cookie, we add a body, we add a post, and we just build in a request. There is no .build at the end, but it's pretty much a builder. It's also typical for FP libraries and APIs to provide a basic, initial, or default way to create data and build on top of it. I've seen this Unison example a while back. So in this example, we have an album, right? There is name, artist, year, tracklist. There is a simple function that just give a name and artist returns you an album already with optional filled in with none. And then you can go and say, okay, album init. You just pass it just strings and then it works. And then you kind of have a builder where you can say, okay, set year to this one and set tracklist to the other one. So you can omit the first part and don't set, or omit the second part and don't set it. You can mix it around. So that's also kind of builder. And we see something similar in Haskell libraries and APIs. This is JSON library, and you can derive codecs for JSON, right? For example, if you want to have your JSONs via camel case, or you have your JSONs via snake case, you can use it via options, and then the library is going to derive the encoders and decoders using the options. The default options are here. And the value is the record. It gives you all the defaults. Like IDs means it's not doing anything. If these options are true, this option is false. And for example, omit nothing fields means if your year is null, depends if you want to include it in the final JSON or not. So imagine that we don't want to. It's the opposite of the default. So we take default. And this is the record. Like it means that you have concrete instance of a record. It has all the defaults. And then we use the record override syntax. So you say we had this record, which is initial one that was provided, and then we override it, and then we set it to true. Now that I look at it, it looks more like prototype, and I think the next one is going to be prototype, so we'll probably revisit it. It's still somewhat of a builder and somewhat of a pattern. There's going to be other options where people do this with monoids. Monoids is a function programming design pattern. The idea is going to be like default op, and then you're going to say omit fields or something, whatever. You also have similar but slightly different builders in FP. I'm gonna share them on the libraries, even though I cannot come up with an example, but I think it's quite common. You say there is a default, and then you add or combine different things to get the other one. To conclude with builder, I think they're pretty common, like especially in Scala. Maybe not the way the book author or the original community intended it, but builders are builders. In FP world, it's quite common to talk about making illegal state not representable. So instead of having builders and constructors, we talk about smart constructors. The idea is to focus on making functions and APIs for creating only valid or validated values that can be safely passed around afterwards. So if we look at the Unison example, here you can set the year to anything. But you probably don't want that. And if you provide an API for users and you don't want them to have invalid albums, you're going to provide a smart constructor that's going to validate that the year, for example, is valid, or the artist's name is not empty, and then the constructor is going to return either a valid album or nothing, or throw an error in whatever way that your language, your library, or ecosystem wants. So prototype, specify the kinds of objects to create using a prototypical instance and create new objects by copying the prototype. This is what we saw with the JSON library. The default options, some record with defaults. We copied it, or we used it as a prototype and updated only what we needed. It's quite a functional pattern as well. Even the distinctions a bit blurry for me. It doesn't matter. The copying data is a bread and butter of functional programming. Some have it baked in. But Scala, for instance, has case classes, and these case classes have a copy method that's given by default. So you have we look in the documentation here. So we have a message with one thing, and then we say message copy, and then we change the sender and recipient, and we get a new sender and a new recipient, but the body stays the same. So in this case, it's not really a prototype, it's just an example, but you can imagine the library once again having a prototype, something that has shit ton of fields or has some bunch of defaults, and then you use that and you copy and make new things. And in theory, it's only the thing that's copied is copied, and the rest should be shared, and it's all amazing. Structural design patterns are about organizing, structuring, and restructuring objects and class. So once again, a small disclaimer, because we don't have those outside of OOP, we'll have to be more abstract and think in slightly different terms. I think we should focus on APIs and something like gluing code together. And to keep it interesting, we'll mix in various approaches. If you can recall, when we started with Abstract Factory all the way in the beginning, we already saw a couple of interesting looking functions. In this case, I'm only keeping the function signatures. As you can see, it's not as simple as pure mathematical function from an integer to another integer or boolean. we have something more interesting. There's some monad beam here, there's BE on the left of double errors, but not on the right. There is some M that we keep in the result and the list of product. In other case, we have monad IOM, which is different. There's some commonality, there is something monad. But then on the other side, we have reader T, but still we have M and M. There is something more going on here. In Haskell, there is plain I/O, MTL and transformers, custom monads on top of all of those, I/O and reader T, RIO, unleafed I/O, services and handle patterns, free monads, free simple, extensible effects, fused effects, F, effectful, clef, polysemy, bluefin, and many other effect libraries and libraries to organize the code. Remember this as we go along, and remember this when somebody says that there is just plain functions in functional programming. Adapter converts the interface of a class into another interface that clients expect. Adapter lets classes work together that couldn't otherwise because of incompatible interfaces. In the simplest case, an interface could imply simply the data we move around. So imagine we have a module responsible for payments. You need to update to the latest Stripe API that have some breaking changes, but you don't want to or you're not allowed to change the SDK module. So we need an adapter. So we have some function getInvoice. It takes a user ID, it takes a status, and returns IO of a list of invoice v1. We sort of skip over IO before, and I don't want to focus on it too much, but the idea is that we describe a computation. We say that when somebody executes getInvoice and pass user ID and a status, then they're gonna get a list of invoices of this version 1. That's it. Somehow we want to provide a slightly different version, the one that returns invoices of version 2. It could be other way around if you think about it. You want to convert from 1 to v0. Doesn't matter. Just different version of an interface, different version of the data. One thing we could start with is the function that goes from one invoice data to another one. Some function adapt that takes invoice of one type and converts it to another type. For example, I don't know, created date was removed and now you add it back. Or payments used to have one currency and now they're all in USD and you need to convert it. It doesn't matter. Just think of it as some mapping from one to another one. So we have one function that used to be before the other function, and we kind of want to adapt them together to have different interface for our users. It's not as simple as composing two functions together, so let's just sketch it out. But the idea is that you call one function, then use another function that adapts this thing, and you have an adapter. Our adapter is gonna call the previous function with the previous version, but because the parameters are the same, we need to pass them to the previous version. Then we're gonna get a response of version 1, the v1 response. And then we have a list of invoices. We need to modify each one because it's a list, and we're gonna apply with a function to map each invoice of one version to another one throughout the list and return this list. And because conceptually we adapt from one interface or one type of data to another one, I would argue that we have an adapter. Alas, it's quite a boring one. A more interesting interpretation of an interface is not data, it's about library and internal APIs. The interfaces, the I in the API. So the APIs that we actually use to code with. And I'll just read myself. There is no one way to write Haskell code. Even in the same code base, it's quite common to have a mix of approaches. For example, you just started a new service with a new fancy framework, of course, why not? And you need to integrate it with libraries that were there before, either internal ones or external ones that use some different older frameworks or approaches. Our simple old boring API is getInvoice that returns IO of list on invoices. API, or the glue in this case, is just plain IO. It's provided by the standard library or just by Cat's library in Scala or whatever. But we want to integrate it with a new service, and this one uses monad transformers. It's just one level fancier. It doesn't matter. I think it's going to serve a good purpose. So imagine we want to use resource T. If you haven't seen this before, the idea is that resource T provides the ability to pass and read the env. In this case, env is an arbitrary name, is a data type. It could be database configuration. It could be, in this case, we have Stripe, so something like Stripe keys, URLs, and whatever. It contains the stuff that we want to pass around, but we don't want to pass around by hand. As you might remember before, we said, oh, just functional programming and pass everything by hand. It gets boring after a while, and you don't want to use just IO, you don't want to use other stuff. So one of the things that people get into first is going to be resource T. So imagine we start using resource T and we need to integrate it with IO. It's a common thing. You can do it manually, but nobody wants to do it. So there is a function just for this. It's called lift.io. It's provided in the standard library. So it goes from the function that returns IO into some whatever m, in our case resource t, as long as there are some instances. As long as somebody done the work for us, there's not much work for us to do. Note in this case it's very simple, and it looks kind of weird that we have get invoice 2 that pretty much equals data invoice and we wrap it with lift.io, but this is an example. In the bigger cases, depending on the context, complexity, your team, this could be handled differently and kept even more abstract. You could avoid get invoice 2 altogether and then use lift.io plus get invoice whatever you needed. If you have multiple resource t and you need to connect just one function with get invoice that returns IO, you can easily use lift.io and add it and use it together. Easily is oversimplified. Some people don't like it. Sometimes it's not easy. Sometimes you don't get instances for free. So there are other alternatives and abstractions that people prefer to use. For example, there is unlift.io, a library that provides different type classes and utilities for unlifting monads to IO. So it's different, and in the examples you can see that there is read file, returns IO, and then read okay, it's a pretty good example. So if you're interested, you can look in the documentation, and actually documentation is a good way to start, because it all depends. Depends on what you use, depends on what you want to use, and how performant and how ergonomic you want to do. For example, if you look at Effectful, one of the popular effect libraries, go to documentation, there is a whole section about integrating with existing libraries. And they have 3 different examples, and you do what the documentation tells you. So we already seen there are multiple techniques and approaches, and even within the same libraries there are different ways to do it, but it still has adapter vibes to all of this. Bridge. Decouple an abstraction from its implementation so the two can vary independently. I think the idea of the pattern is to use composition instead of inheritance, to decouple the high-level interface that the clients interact with from the concrete implementation details. Luckily, inheritance is not a problem outside of OP, so we can decouple the public interface from the private in many different ways. For example, if we talk about libraries and APIs, one common approach in Haskell and PureScript library design is using the internal module. I hope it's clear by the name of what it does, but let's look at examples. If we look at the byte string library from Haskell, the public API is this, data byte string. This is the documentation. It tells you how to use it. If there is some APIs, how to create empty byte strings, basic interface, basic operations, substrings, predicates, whatever. The public API, right? But if we look at the data.bytestring.internal, that's the semi-public. Does expose it for the user if you want to use, but the contract is that it's a lower level API and it's implementation detail. The internal APIs is not stable and not meant for casual everyday usage. It's meant to provide flexibility for advanced users, and it's just social contract. If you open the containers library and open any container like int map, the internal, it says it's eternal, be careful, and so on, so on. The approach is not really a bridge, and it's not everybody's favorite approach. Doesn't solve any problems, is just one example. I don't think there is any interesting generalization or patterns for bridge. Composite. Compose objects into 3 structures to represent part-whole hierarchies. Composite lets clients treat individual objects and compositions of objects uniformly. Trees and recursions are native to functional programming. For instance, there are design patterns for traversing and recursing over nested data structure called recursion schemes. I think it's too complex and too specific to represent composite, and we can get away with something simpler, but highly recommend to check it out. There are many talks and many papers and stuff. I think we should talk about type classes and use type classes to model composite. Let's just focus on having uniform interface for components and composition of components. Imagine we need to have a printable interface. I know, very fun, but bear with me. First, we declare a class, the type class. Don't think about OP classes. Think about Rust traits or something like this. There is something printable, which has a print, and it can print this whatever A we have. We can implement the printable instances for anything that needs to be printed, pre-printed. Let's rely on the default PureScript show for a number and return a string in quotes. So if we have a number, we can print it by showing it. And if we have a string, it's already printed, but let's just add quotes around it. There is no string interpolation, so we just concatenate quotes from left and right. And if we have an array of printable things, we can print them all. When we write the instance, we need to say or declare that if we want to have a printable array of some elements, we need or require the printable for all of those elements. And in implementation, we print all the elements. We use map, which relies on the functor instance of array, a map function. But I think map is getting quite common now. The idea is that we print all the elements and then we use intercalate function, which puts comma between each element, between each string, and then we add square brackets on left and right. And we got our array printed. So let me be a compiler for a second. You just have to trust me. If we print a number, we get number in quotes. If we print a string, we get a string in quotes. And double quotes. No, just one quote. Kind of no difference between number and string. But if we print array of numbers, we also get it pre-printed. And if we try to print array of booleans, it's not going to work. As you can see, the interface for things and composition of things is uniform. And to wrap up this example and make it more treeable, let's do a printable JSON. It's going to be a mix of printable and not printable types. I'm too lazy to type all out and to test the quotes, but you have to trust me. So JSON is either null or boolean with a boolean, number with a number, string with a string, array with array of JSON is interesting because we starting to have more interest in composite, and the same for object, which can have JSON as values as well. Right, so if we want to make a printable, we need to have another instance. Can fall back to the stuff we had inside. So for null, we didn't have anything, so we just do null. For boolean as well, I'll skip it. But for number, we can rely on the print of the number. It's nonsense for JSON because usually the number, you want to keep it as a number, but this time it's going to be in quotes. But as an example, bear with me. With array, it's also going to reuse the array. And with object, we'll have to print pairs. You're going to print the key and then print the value using the same instance. If we focus on the way the arrays and objects are handled, this looks quite a composite to me. Decorator. Attach additional responsibility to an object dynamically. Decorators provide a flexible alternative to subclassing for extending functionality. My favorite use of Decorator is to separate business logic from production-needed bells and whistles, things that help observability and performance, but can swallow the core logic if not tamed well. Let's revisit the tagless final processor that we used a while back. We had the payment processor interface that has process payment and refund with two implementations, one for PayPal and one for Stripe. The actual implementation doesn't matter. The idea is that we have processor and there are two ways to process via PayPal and via Stripe. So if we want to add metrics without duplication and polluting the actual implementation or core logic, we can add a new implementation of the payment processor to enhance the functionality. Let's start with Meteor processor. It's going to take some other payment processor and some metric service that's going to be responsible for measuring and sending stuff to some registry, some Prometheus registry, for example. Implementation could be as simple as calling the metric service measure method and wrapping the underlying process payment, and similar for other methods. In other words, if we pass PayPal processor or Stripe processor, we're going to use the process payment or refund payment on that processor, and then we're going to do measurement on the top or around it. And similar with caching, right? We can add some caching layer, we check with the cache, and if it doesn't work, we go to the Stripe or we go to PayPal. And this is how the usage of Decorator is going to look like. We take the original processor, for example, PayPal, and we wrap it or decorate it with Meteor processor. And in case of Stripe, we also add the caching and then the meters. We can mix and match as much as we want, which makes Decorator quite useful and convenient even outside of OOP. Facade. Provide a unified interface to a set of interfaces in a subsystem. Facade defines a higher level interface that makes the subsystem easier to use. To be honest, I don't think it's a real design pattern. At least in my mind, it's just good design, just good manners. I don't think it's even worth talking about it here. Flyweight. Use sharing to support large numbers of fine-grained objects efficiently. This one is also a normal phenomenon. In my naive and optimistic view, in the presence of immutability, we often get something like this for free. Imagine we have some kind of data. For now, it's just a wrapper or an integer, but some expensive data, something really expensive to calculate. And imagine we have really expensive calculation as well. The function make expensive value is doing something really expensive. It just wraps an integer in the expensive value, so it's not very expensive. But what we have here is we have a trace. This is a debug function in Haskell that's going to take when we are evaluating this part, when we are here evaluating, we're going to see a log that's going to say, oh, create an expensive value. So each time this is calculated or instantiated, we're going to see this log. Make sense? So now to the third level of user imagination, we have a program that calculates or instantiates or whatever the expensive value wants. The X is going to have the expensive value, and then we print it. So it's not lazy, it's going to create it. There is no way to print something in case unless you have it, unless you evaluate it, right? We have the lock only once. The point is, if we create an instance of something expensive, it makes sense that it's created only once. But the cool thing is, if we want to create a whole list of those, just a whole 5,000 of those, it will still create one instance, and it's still going to create an expensive instance once in the logs. This is a slide, so you have to trust me, but this is it. This is still going to print the bug once, and the initialization happens once. So we get a built-in Flyweight, which is pretty good. Proxy. Provide a surrogate or placeholder for another objects to control access to it. So I think using proxy is structurally similar to Decorator, but instead of providing an additional functionality, the idea is to restrict access, sometimes add lazy initialization and so on. The ways that clients or users might view it different or treat it differently, but I don't think it's huge of a difference. I think if you're looking for proxy, you can look at how the Decorator is implemented or how the functional language approaches Decorator and do something similar. Okay, behavioral patterns. Finally, a set of patterns that have nothing to do with classes and objects, right? I guess we'll see. We start with a chain of responsibility. Avoid coupling the sender of request to its receiver by giving more than one object a chance to handle the request. Chain the receiving object and pass the request along the chain until an object handles it. When I think about chains and fallbacks, I immediately think about options. Those functions return option. It means that we don't do any executions, we don't go to any database in this case. We'll talk about this later. Imagine if, for example, we have a list of payments, we have a list of Stripe payments, a list of PayPal payments, and we try to get a head or first element. So if there are no payments in the list, it's going to be none, and if there is a payment, we can get the first one, similar for both cases. Option is the functional or data view on nulls, something like that. But the idea is, if you have an option of payment, you either have some payment, or you have none, or you have nothing. We can chase those together. For example, if we have first payment via Stripe, and then we have second payment via PayPal, either of them can be optional, either of them can be nothing. We can do first or else second, and then we can add some fallback or default value with get else. So if first one is some payment, then we're just going to return the Stripe payment. If the first one is none, there is no Stripe payment, then we try second. And then depending if there is one or not, we go to the default or not. It is a chain. We chain a few things until we get some payments, right? This is not much of a chain of handlers. So let's look at something more interesting. Imagine we need to extract a version out of a string, but we are dealing with questionable vendors or or providers. Some return v11, some return without v, just numbers, some return dates, and so on. So we want to create a list of parsers and go through them to get the proper version. Here we have a couple of functions that try to extract some version out of a string, and each one tries to do it its own way. Either the first one tries to get the semantic versioning, the other one tries to get calendar versioning, and so on. Bunch of functions, each one tries to parse in its own way. So we have some function now, parse any, that also goes from the string to option of version, takes a string, and then it passes the string to each one of the functions until one matches. Conveniently, we can use the function collect for some, and if it doesn't, it returns none. So if we play the compiler again, if we pass this, it's going to work because our calendar is going to match and it's going to return some, and same for all the other cases. But if we pass some nonsense string, it's going to go to the first one, it's going to fail, it's going to go to this one, it's going to fail, it's going to go to this one, fail, and so it's going to be none at the end, another version. I hope this makes sense. It's going to get better from here. This is one way to organize things with a list and collect first, but this is just Scala specific. There is something more generic and more explicit. We can use beautiful operator instead of this. This operator comes from the semigroup K-type class. Actually, it doesn't matter where it comes from, and the name also doesn't matter. It's quite common. We don't go too deep into parser combinators, but this would be a really fitting detour. In parser combinators worlds, they don't use options because we need meaningful errors. They do use plenty of type classes and operators to chain parsers together. So if you're interested, you should consider exploring any Haskell library, but if you open megaparsec, one of the popular ones, we should see alternatives and operators like this quite soon. if you look at primitive combinators, yeah, so we already have try, parse let, or lexical, let or lexical, let or lexical. You can see that in a parser library, something like the chains of responsibility is going to be common. If you want to see more, see more. Let's go back to our payment example. So if I want more than just parsing and working with simple stuff, if we want arbitrary handlers of request, we can use IO along with option. Things about IO as a way to describe computations. We're gonna talk about IO just in a sec. Start by imagining multiple functions that do some fetching. We'll start with fetch stripe, you execute it, and then optionally get a payment. So we started with a simple case where we just option payment meant we extracted with array or something. But now we do actual execution. We go to the database, we call external service, we call Stripe or PayPal with SDK. It doesn't really, it's not really different. So we can just change them with or else's again, or we can change them with operators. Depending on the language, you might need some special sugar, special libraries. This is one way to do it. It's from the mouse library, not from the cats in Scala. The second case is via option T. You cannot simply say IO option and then combine those with this operator. You have to explicitly wrap it option T. All depends on the language, all depends on the libraries, but the idea should be the same. We have chains and we we have multiple optional things or things that have instances of alternative. So if you're thinking about chain of responsibilities, in your mind you should think about options or alternatives. At least that's what in my mind. And to nail the point, one of the Scala HTTP libraries, one of the functional Scala HTTP libraries uses something similar to chain services, like actual request handlers together. If we go to the documentation of services, we can see that we have some tweet service, we have hello world service, and we chain them together with the same operator. So if imagine you have a route and the route is like /tweet and the other one is /hello. If the first one matches, we go to the first service. If it doesn't match in the first one, it goes back and the second one tries. And usually at the end you have not found. So this is a good match to chain responsibilities. Command: encapsulate a request as an object, thereby letting you parameterize clients with different requests, queue or log requests, and support undoable operations. So we're gonna ignore the last part for now. Otherwise, this is IO, or task, or effect, or whatever your language or library calls it. This is represented by some data type to describe and pass around computations. Sometimes we call them effect flow computations. We've seen IO already multiple times, but let's just use effect from PureScript. It's exactly the same as IO. Let's start with a function that takes arbitrary command, arbitrary computation, and repeats it n times. To make it clear, we can add a log. We're going to compile in here again, but it's going to allow us to differentiate the stages we as a console, even though it's a fake console. So let's go step by step, even almost word by word or thing by thing. First of all, we have function definitions. It says for all a, it takes an integer, takes effect of a and effect of a. In PureScript, we have to be explicit about polymorphism. You have to say that for all a, we mean that any effect a, doesn't matter effect that returns integer, effect that returns option of an either, of an integer, of a string, of whatever domain, doesn't matter. Whatever you pass us, that whatever is going to be the result as well, because we're going to return the same thing that it returns. In the body, we say if n equals 1, probably should be something like n less than 1 or some error. It could be 0, doesn't matter. Then do, we have a do block. It's quite common way to chain and organize your IO's task or effects across the languages. It's the same in PureScript, same in Haskell, same in, it's 4 in Scala, but it's quite the same. In Unison, it's similar and so on, so on. So we have the do block. The first thing we do is log done, and then we execute the task. Whatever the task returns is going to return as well. This is going to be more interesting later, because in the else case, if n is not equals to 1, probably, hopefully n is bigger than 1, is going to do doing whatever show, and then do the task again. In this case, we throw away the result. So the other way to do this, probably explicitly, we have to say that we ignore the result, we throw it away, which is better. Or we have to say void, doesn't matter, just a questionable repeat, right? Because if you repeat and each operation returns something, what do you do? In this case, we're just gonna do the last one, because we're gonna repeat with n minus 1, and we're gonna go repeat again until we get to the last task, and whatever the last task returns, this returns. Now let's compile it. If we put repeat 3 is gonna log doing this one first. Execution here is gonna be doing 3, then it's gonna go to the task, right? I don't know what the task should be. Repeat 3, just, I don't know, let's just log, I don't know. So because our action now is logging again, I know it's very creative, I'm sorry. It's just gonna say, I don't know, then it's gonna loop again with repeat, n-2, 3 minus 1 is 2, it's gonna log doing with 2, this one. Then it's gonna be the task again. We call the task because I was very original. It's gonna say, I don't know. Then we're gonna repeat it again. This time the 2 becomes 1. We go to this case becomes done. We print done. And then the last thing we need to do is the task again, and it's gonna say, I don't know. Sorry for the shitty example, but I hope the idea is clear that the effect or IO, these data types, as long as we can express the computation with data type, we have the ability to pass any command, anything with data type. And I think it's pretty cool. But it's just a very simple example. Let's do something more complex. Let's go back to our domains. If we return back to the payments domain and sketch out a more complex client, here we use a service pattern. It's not very documented and not very restrictive, but if you're coming from OOP world, it's pretty much just an interface. So we have some type, an interface with two functions, fetch payments and prepare invoices. This is an interface, and the concrete implementations is going to have fetch payments and prepare invoices implemented. Pretty convenient and simple way to bundle things together while keeping things more flexible without having full-on blown classes and stuff. And here we have more realistic example of passing commands. Not production ready, it doesn't have exception handling and retries, it doesn't have the rollback or undoing operation. It's not really a command, but it covers 80% of the use cases, if not more. We can pass different implementations of tasks and actions to the client, and then the client decides in what order to execute those, how many times to execute, and whatever else. So we pass fetch commands and prepare invoice. The client, in this case, our own implementation decides, okay, we call the fetch payments once and we get the payments. And then imagine we have a list of dates that we need to parse. In this case, just a list of 3 dates. And then we say for all of those dates, for the whole list, prepare an invoice. So we passed one command and we can execute it 3 times. If we want a fallback, we do fallbacks. If we want retries, we want retries. If we want to undo, we cannot. But if this is not enough good news, we can integrate this with the techniques used to replace the interpreter. So, interpreter. Given a language, define a representation for its grammar along with the interpreters that uses the representation to interpret sentences in the language. I'm pretty sure this is the most beloved design pattern among functional programmers. For instance, EDSLs, embedded domain-specific languages, are very popular. And this is like one of the go-to examples for selling functional programming. The overlap between this OP pattern and the functional programming patterns is pretty significant. We've already seen a few interpreters in the previous examples, but let's start with an alphabet. Expressions. We start with defining expression and 2 operations. 2 expressions. One is add, which takes left expression and right expression, and add is an expression, and literal. For now is just an integer, which also extends expression. And then we have 2 evaluators, also called interpreters. One takes an expression and returns an integer. We take an expression, we pattern match on expression, and if expression is literal integer, we just extract it, it's just an integer. And if we are adding left and right, evaluate left and add to evaluation of right. So if the expression is also addition, we'll have to evaluate that first, and we go evaluating and evaluating until we get to the literal. We can go back and add. And we also have a different evaluator for pretty printer. It takes expression again and returns a string this time. For literal, we just integer becomes a string. An addition in this case is pretty printing left and right and concatenating those. And the plus is a plus, it's a string plus, not the addition plus. And when we have operations ready and interpreters ready, we can represent and interpret sentences like this one. We can add literals and evaluate it, and we can also pretty print and do whatever we want with what we have. The problem is it's not production-ready example. There are plenty of issues. It's hard to extend and add new operators. For now we have 2, but imagine if we want to add multiplication, or we want to have not just integers but boolean or whatever else. and supporting the type literals is a whole new problem, right? But this should be a good starting point. Everything goes and grows from here. If we hop just a few learning steps ahead and look at real-world examples, we'll be talking about free monads, tagless final, we'll still be talking about interpreters. And it's especially common in Scala. If you look at one of the popular Scala libraries, it's called Dubi for SQL or persistence, it uses free monads. If you look at the description, the interesting thing is right in the first paragraph of the introduction to the library, provides functional ways to construct programs. And when you construct them, you have to interpret it. So that's our clue. If we go to the examples, for example, connection to a database and scroll, we build programs using connection.io. And if we scroll just a bit, we should see that all of the Dubi monads are implemented via free. And then it says that we can run them by transforming them, aka interpreting them. And the next sentence says that out-of-the-box Dubi provides an interpreter from its free monad to whatever it is. When we look at the interpreter, which is the default one, doesn't matter what it says. When we have a program, we interpret it. Right there, one of the most popular libraries uses interpreters, and it's really fun. Technically, it provides an interpreter from its free monad to something more generic than I/O, but I hope the point about the interpreter is clear. And even though it's not alphabetical, while we're here, let's look at the visitor. Visitor represents an operation to be performed on the elements of an object structure. Visitor lets you define a new operation without changing the classes of the elements on which it operates. Super common in FP presentations and blocks to compare visitor to pattern matching. Here we have a typical visitor interface. We can visit PayPal, visit Stripe, or visit a bank transfer, depends. The pattern matching example is, instead of that, we have a payment, and then we pattern match on the payment. If it's a PayPal payment or Stripe payment or bank transfer payment, we do the rest. So that's it. A visitor next to the pattern match, then you're supposed to laugh because a design pattern was invented to compensate for lack of language feature. But the thing is that life is not that simple. Not every functional programming language supports some types and pattern matching. So this answer is not really an answer, even though it's incredibly funny. So what do languages without pattern matching do? They can get away with simple church encoding. Probably C needs to be capitalized because it looks weird. Or another one that I don't know how to pronounce, unfortunately. So which type of encoding you need depends if your language, if it's typed or not. But for our example, we're just gonna use Scala, and we're going to use something that wasn't really needed. If we have an option 3 and we match, and we do a pattern match, we can say that if the case is sum and we have some integer, we print that you have an integer because it's wow. If we have case none, we pattern match, and we do something else, we say, oh, you got none. So the thing, we have two cases. One, if we have an integer and then we do something with this integer. In this case, we don't really do anything. So we can include it and say right here, we're going to replace an I with an integer. It's going to be awkward, but we're going to put it right there. Imagine it's used somehow. What we really need is we need to say that, oh, in case of I, we do one thing, and in case of none, we do thing. So actually what we need is just two functions. A function to deal with a none case and a function to deal with a sum case. Partially for this reason, partially not for this reason. But we have a fold in Scala that we can say that if you have option, again, of 3, and the fold takes two functions. First it takes function, it's named, they're named arguments, so we can be more explicit, but it's just a function. Or second function, in Scala, it takes two different sets of parameters. In this case, it's, imagine they're separated by the comma or by a space, doesn't matter, it's just the fold takes two functions. So pattern matching, function programming, not really needed. We have the encoding in this case. If we go back to visitor and talking about visitor, we've seen Dubi in the previous section. And if you go to the source codes, actually, here's the funny thing, there's interpreter. Remember from the previous part, we go to one of the implementation, it's gonna talk about visitor. The thing is that even though Scala has pattern matching, sometimes it can be more efficient to use a visitor. Or maybe it used to be in the past, but the point still stands. Also, Java 21 comes with pattern matching, or it already came with pattern matching 4 or 5 versions ago. So we'll see if it's time for visitor to retire or not quite soon. And now we're gonna have a cool transition in the talk about folds. Iterator. Provide a way to access the elements of an aggregate object sequentially without exposing its underlying representation. Multiple things here. And it really depends on the aggregation we're talking about. First, we can talk about foldable and traversable type classes. Let's start with foldable. Imagine we have a list of whatever. We can use a function length on it to get the length of a list. We can use a function element and get or check if the element exists in the list. We can use a fold with operation, for example, minus initial element 0 and the numbers, and perform the fold with this operation over all the numbers. We can also sum the numbers and so on. All of those come from foldable, and usage is not limited to just lists. We can find foldable instances for all sorts of things. We can even derive those for free. For example, in the docs, if we have a tree, it can be empty, it can be a leaf, it can be a node with multiple trees, we can derive foldable, and then it's going to behave quite similarly. We can get the lengths of things, we can get the elements, and so on. And if we scroll a bit, traversable, that extends or builds on top of foldable, this one is even more fun. Fundamental function for traversable is traverse. Imagine we have a list of strings, 1, 2, 3, they're numbers, but they're strings. Strings of numbers. If we traverse with the function readMaybe takes a string and extracts an integer out of it. And if it succeeds, it returns just of an integer. We see an optional, it's the same as sum in Scala, or none or nothing in case it cannot. So if we have a list of strings, we traverse with readMaybe, we get the maybe of a list of integers. If all of them succeed, like in this case, we get 1, 2, 3, we get a successfully just a list. But if we have bad strings, the one of them is not an integer. XY cannot be parsed. It's going to be a none. It's going to be nothing. So the whole list of strings cannot be parsed. Just because of one element, it short circuits and returns nothing. This is quite powerful. Might not be as obvious, but it allows us to short circuit. It allows us to deal with more complicated things. For example, if we have functions to fetch users, we've seen IO before. It's some function that takes an integer. Let's say it takes user ID and goes to the database and returns the name of the user, some user data. If we have a list of integers, we can traverse with fetch user data on all of those users' IDs and sequentially return all of them. The thing is, if IO fails, in one of the operation fails, the whole traverse is going to fail. So those two, foldable and traversable, play a vital role in iterating over things in functional land, but I wouldn't stop there, because we also have optics. They allow us to deal with pretty much any sort of aggregation and complexity. Incredibly a lot to cover here, but here's my favorite example. Imagine we have warehouses with stocks, and our task is to update all existing shoe stocks. 2 warehouses here, one in London, one in Berlin. Berlin is not very exciting. Each one has inventory. In this case, just we're looking only at shoes, and this is a list. Only this one has a stock, and it's possible that we don't have any stock. So a lot of optional things. The inventory is optional, like we have in Berlin, and also name and stock and all the other things. I don't know why we have a brand. That doesn't matter. Just the stocks is optional, inventory is optional. Way to describe this could be something like this. We have ignore underscores. It's one of the conventions to make the rest look nicer. We have response, that warehouses, list of warehouses. In this case, it's also only one, as you can see. Then we have inventory, as we have inventory here, and it's maybe, it's optional. Then we have shoes, which is a list, this one, and then stocks is also maybe stocks, optional. Imagine we need to go through all of this to update all of this, and all of this optional. Just think about it. How would you implement it in your language of choice or your paradigm of choice? Let's make it a bit smaller so we can see it, but we don't actually need to see it. We're not going to talk about basic derivations, basic lenses, basic things. We have different types of optics, and we need to compose them together into a bigger optic. For example, we start with, let's call it all shoes. Just simple. Imagine that we need to just only go to up to this point or up to this point. We start with warehouses. You see, here we had underscore, but here we don't, because we're talking about optics, and that's why it's different. Those are going to be derived and provided by the library. We want to look at all the warehouses. In this case, we want to look at inside the response at the warehouse. It's not here, it's not part of the JSON, it's part of the Haskell model. We look at all the warehouses. Then we have a dot, which is composition, and then we have traverse. This is a different traverse. I'm sorry for the naming if you haven't seen either of those. But this is traverse that tells us, look, we look at the warehouses. Now we need to look at the list of warehouses, which is not that different from the previous traverse. That's why they both come in the same section. This might remind you of JQ, by the way. If you've seen JQ before, we're not that far off. Then we need to look at the inventory part of the warehouse. And imagine we are inside the warehouses, we're here. So we now need to look at the inventory. So we just say inventory. Now, the interesting thing is that this is a maybe. So we add this field. but we're not in the inventory. We need to go through maybe. You can say traverse because traverse is very powerful, but you can also say just. It says that only go here if this is not a nothing, if it's a just. So now we're in the inventory. Now we're here. So now we look at the shoes. And the last thing, if we want to be inside the shoes, we have a list again. So we just say traverse. Here we have all shoes optic, an optic that says if you have a response, I'll get you all the way down to shoes. This is our optic, that's this. The fun thing is that it's all composition, it's all just functions that we compose. We can have, I split that so it fits in the slide, and I've done it before multiple times. So split this on purpose, but you don't have to. You can be all in one optic. Often convenient to reuse those and have them more flexible. So if we want to look at the existing stock, if we want to go from the response all the way to the stock, we start with all shoes because we are already almost there. We are here. Now we need to go to the stock field, and then we need to go through the maybe to the stock. Say stock, and then we say just. And now we have an optic existing stock, then goes from response all the way to the stock. It goes from whatever response all the way here. And if we have more, it's going to point to each one. The cool thing, if we want to modify it, if we want to do some action, there are functions like over. We say over existing stock, right? And we say something like subtract 1 or -1, just trying to be fancy, and then warehouse response. So if you have some warehouse response, this is an example. With bunch of stocks, we can use over existing stock optic. That's going to go and update all the stock. And if this is not cool, I don't know what is. Technically, in this example, we are working with underlying representation, right? We have to go and say each field. We need to know what's internal. But if you think of those snippets as a library internals that only expose all shoes or existing stock. So here is our library limit. Imagine as a user, as an API user, I only see this and I only see this. I don't see any of inventory shoes traverses. I don't need to know. I don't care. You just give me 2 optics. You give me this API and I use it. And then if you're ready for it, internal representation changes. For some reason now we don't have inventory. We have inventories. And this is now a list of inventory. I don't know. Imagine you have 2 shelves or something. This is going to be an array. And guess what? We need to change this. Just a name change. And instead of just, remember we had list before, we just say traverse, and that's it. This didn't change. This didn't change. The type was the same. The type said, you give me response, I go all the way down to stock. This doesn't change. This doesn't have to change. The user doesn't care. I think it's pretty good. Mediator. Define an object that encapsulates how a set of objects interacts. Mediator promotes loose coupling by keeping objects from referring for each other explicitly unless you have I think it's similar to the Facade. For me, not a real design pattern, especially if I talk about it after looking at optics. You just don't write spaghetti code. That's it. You don't need design patterns like this. Memento. Without violating encapsulation, capture and externalize an object's internal state so that the object can be restored to the state later. In the presence of immutability, the state cannot be modified, so there is no encapsulation to violate. In this case, history, when we capture the state or we create a history, this history can be just a list of states, a list of previous states. I used to work in a company working on the graph editor with PureScript, and we needed to keep a history of states to support undo. Our model for the app was some, let's just call it editor. It had a current state, which we call editor state here, and then the history was just array of editor states, not a list, because it's JavaScript array are fine in this case. And this is a Memento, right? Part of the Memento for the interface, we need something like undo, and then it goes from editor to editor, because the editor is still immutable as well. State update, state management in the PureScript that takes care of this, but the idea is if you click undo, the button undo, the current state goes into the history. The previous one from the history goes into the current state. It was more complicated, or maybe less complicated, more ergonomic. We also wanted to support undo and redo. We wanted to go back in history and force in history, control that and control shift that. We could have used array, but there is already abstraction for this, and it's called zipper. You have an API like this. You can extract current element, which is always present, and you can also get the previous element. It's optional, right? Because you might not have it, and the next element, because it's also optional. Observer. Define a one-to-many dependency between objects so that when one object changes state, all its dependents are notified and update automatically. This makes me think of functional reactive programming, but I don't really have much experience with it production-wise, so I cannot come up with an interesting example. However, I do have experience with simpler functional streams, like fs2, that provides primitives like topic and signal to implement the publish-subscribe pattern and the other ways to define dependencies between objects. First, we create a topic. Because we want to create one topic and reuse it, we need to do it this way via flat map, similar to the way we use IRF, the one we looked at a while ago. So we create a topic, then we create a publisher. Publishers, I don't know, some whatever stream from somewhere else. It's not a function, it's just coming from somewhere else. They have some data and it publishes into the topic. And then the subscriber takes the topic, subscribes to it, and just takes one thing for now, and that's it. Because illustration purposes, and then we run them concurrently. This is also running them concurrently is an IO, that's why we have a flat map, create topic, and then run them concurrently. So we have a publish subscribe with fs2, which is an option. The other option makes me think about events or API like this. So imagine web events, imagine button clicks, form updates, key presses. There is some event handler that on each event does this, and then you just assign it somewhere else and you have, event handler. I think this might not be clear. If you never saw this before, let's look at example. Let's look at PureScript and then let's look at the docs and then look at something real. My go-to example in PureScript is PureScript React Basic. If we look at the docs, if we scroll just a bit, event handler is a function from some synthetic event to unit. It's a verbose version of what we saw. Just imagine it's an event. We create event handler by providing a function that based on the event handles it. And now let's go one level deeper into the concreteness and look one of the example. I had this library for looking at SHA-CN and demonstrating a simple form. One of the forms is password, right? You have input password, you have HTTP form, you have input component, and input one of the props, one of the React props, one of the input is on change. Right? If your input changes, we create a handler for target value, and then we remove an error and then update credentials. We set the password to a new value. If you don't think that either of those fits an observer, just wait till you see what I have for the next one. State. Allow an object to alter its behavior. When its internal state changes, the object will appear to change its class. Probably the closest kind of functional, kind of backend kind of version of this is finite state machines. Let's do a straightforward example. There are many ways to implement a state machine depending on the language, use case, and the rest of the code. There are libraries for this. Same domain, payments. We start with a draft state, and then you can send an invoice, and then it becomes in a send state. And after invoice is sent, you can either pay and get to the paid state, or cancel and get into cancel state. We can model it with an enum of states, which draft, send, paid, or canceled, and an enum for events, which is send, pay, and cancel. And then we're gonna have some state machine. In this case, it's simple pattern match. If there is expected state like draft and then event is sent, we do something. If the state is sent and then there is pay, we do this, and send, we do that. And in all the other cases, invalid state, some invalid condition happens, so we want to do whatever. It's a programmatical error, whatever error, it's an error. And depending on how we implement this, it might not even be possible. So that's one, finite state machines. Let's take a step back and think of the state more abstractly. There are no objects in FP, so if we are talking about altering an object's behavior, we should be talking about altering the behavior of functions. In theory, we can make the behavior depend on the input parameters. You change an X for Y, and your function changes. Different parameter, different behavior. However, it's talked about in the context of structural patterns a while ago. At some point, we have to start using higher level concepts and ways to organize code, not just plain functions. This is where the concept or ability, or whatever you want to call it, of state comes in. There are different implementations and approaches, but they all have the same interface. There is get, which returns the state from internals of some doesn't matter for now, and s is some state. And put, which replaces the state inside some m, so we have some state here. The interesting thing is that we have some state here, and we have some M here, and this case is unit because you put stuff, you don't get anything back, so you put stuff, and then you can get it back with get. Now let's get to the examples. There is state, data type. This is the most basic one. Get and the put, exactly the one that we saw. There are various states in each effect library. For example, there is bluefin and it has state. This one has some E of effects to it, but if we go to the operation, there is also get. If you ignore all the effects and other things and squint and you pretend that this is nm, it's quite similar. We get the current value of the state, and for the put we have s and also fs, which should be m. We can put the new value into the state. A bit more interesting, right? But I think the simplest one to use as an example, as illustration for now, is going to be monad state from the MTL library. To be honest, we were looking at the interface of monad state before because the state is tightly connected to the monad state, and if they were in the same file, the state is actually a bit different, but the interface is the same. It all applies to all the same implementation anyways. Imagine we want some pay function. First is the type signature. The function doesn't really return any meaningful result, but there is some m it carries around. This m is connected to the monad state. The monad state has an invoice. It means that we can get state, so we can get invoice, and we can put invoice. So roughly speaking, we carry around invoice as a state. That's it. First, we get the state, the current state. And then, because it's we talking about design pattern state, we have behaviors. It depends on the internal state. Internal state of this m, and internal state is an invoice. So if the invoice status is sent, we can say, okay, update it to paid, and then put it. So the m is going to have a new invoice. And then if not, we say pure unit, we say just nothing. This is a very convoluted and interesting way to say that we get a state and then update the state if the previous state was expected. This function is quite abstract. We say that we do not care who or how is going to call it, as long as they implement the monad state type class, as long as they provide some sort of get and put for, in this case, for invoice. They can store state in a single thread immutable variable, in atomic reference. They can store it on the disk for whatever we care. We don't care. And note, if we have multiple operations, if we have send and cancel on top of pay, we can chain them together. We can create a program that sends first, then it checks some condition. I don't know, just checks the date, whatever, and then it either pays or cancels. If you haven't seen this, it might feel weird that there is some weird monad state that we carry around. We're going to initialize it somewhere on the top of the chain of the abstractions. We're going to say that this is initial state, and then we're going to carry the state and update it with each one of the function like this. And then at the end, you can throw it away if you don't care about it, you can act on it, and so on and so forth. So this is state. And to keep this simple talk about state even more interesting, I also want to look at the state from the front-end perspective, from the more functional front-end perspective. We might be getting even more off track, but this talk about state reminds me of Elm. When they talk about Elm programs, they talk about model, the state of your application. They talk about view, a way to turn your state into HTML, and update, a way to update your state based on messages. If you squint, it does alter its behavior when the internal state changes. And even though the basic description of the pattern doesn't mention how the state changes, here in the Elm world, the state changes via the messages. You can see something similar in Lustre, a framework for building web apps in Gleam. The state of the application is stored in a single immutable data structure called the model and updated as messages are dispatched to the runtime, similar to what we saw now. I'm mostly familiar with auth-reducer from PureScript React Basic Hooks, which also has state and actions. And the most interesting part here at the end is state, and each action is handled with the effect. We have some state and the reducer functions acting on this state. So there is a pattern between those three, and this is state, so I think it was important to mention it, even though it's way out there compared to the state in OP. Strategy. Define a family of algorithms encapsulating each one and make them interchangeable. Strategy lets the algorithm vary independently from clients that use it. Finally, I think we have a design pattern that can be replaced by plain functions. Let's start with the first member of a family, the process type. It's a function that, imagine it takes a payment and returns leftover balance. And then we have another one, process PayPal, which also takes a payment and also returns the same balance. So we have a family of algorithms. We have functions that have the same interface. And if we have a different functions that takes one function from payment to balance, and that's whatever it does with it, we can either pass this one or we pass this one. And then the client can use whatever. They can decide on the algorithm and then can use them and change them interchangeably. If it needs to pass a payment processor, so that's it. Template method. Define the skeleton of an algorithm in an operation defining some steps to subclasses. Template method lets subclasses redefine certain steps of the algorithm without changing the algorithm structure. So either I'm getting tired, or this could be similarly replaced with plain functions. We can pass steps via function and be done with it. And if we need something more complicated, we can use one of the many approaches we discussed before. Some more complicated functions. So, to conclude, here we are, and there is no moral to this story.